All right, back at it again. We just finished double replacements. I Aggie engineered this and ripped the top of the paper off where we did the double replacements because it fits under the camera better. So we're gonna roll with it. This whole process is gonna be a little rough around the edges, but we're gonna get better and better as we go. This video will be much shorter than the last one. The last one had the double replacements on it. This is a single replacement video, and so I am gonna show you the long way to do a single replacement net ionic equation, and then I'll show you a quick one of these as well, and hopefully you'll be off and running. Some of you have already probably noticed this net ionic equation practice sheet I'm going over is the same practice sheet I gave you out before break. So some of you had already finished it. I just chopped a couple of questions out of there and gave myself a little more space so I could work through them with you. So if you recognize them, that's why. The assignment I'll give you online has double and single replacement reactions kind of mixed together, and so you'll need to kind of be able to look at them and figure them out. So here we go. So this is the long version of a single replacement, and then we'll jump into the quicker version, and hopefully it'll make some sense to you. So here we go. This is same process, same exact process as the double replacements. The steps are the same. And so the first step is to write and balance the equation. So here we have some aluminum metal. Aluminum at room temperature is a solid. So just like I think on the last video I put states of matter in the first equation. Ultimately I don't care about states of matter, but I want you to be able to see them here initially. So a solid piece of aluminum is going to be reacting with a solution of silver nitrate. So we have an aqueous solution of silver nitrate. Still the hardest step is writing and balancing the equation. Because it's a solution, that silver nitrate will be aqueous. And we've got to predict the products here. So aluminum, single element coming in here. It's a metal, so it's kicking out the other metal. This is the old beating up somebody and taking their girlfriend reaction where silver gets left by himself. Silver all by himself is solid, and the aluminum is going to creep in and take silver's place. So we end up with aluminum nitrate. That's going to be aqueous. How do I know it's aqueous? Because that nitrate is always soluble from those solubility guidelines on the last video. We do need to come in and balance this equation. There's 3 nitrates here. That gives us 3 nitrates there. That gives us 3 silvers we got to put on both sides. So that's step number 1. Write the equation, balance the equation. Step number 2 is to take and write the overall ionic equation. So anything that's aqueous breaks apart. If it's solid, leave it alone. So the aluminum solid, we leave it alone. The silver nitrate being aqueous means that guy is going to dissociate into 3 silver ions and into 3 nitrate ions. When they dissociate and they're aqueous, they have to have charges on those individual ions. They're no longer attached to each other where they were neutral. Now they're separated, and when they separate, they have their individual charges. Good. Product side, those 3 silvers are solid, so we leave those together. And then the aluminum nitrate here is aqueous, and so it separates into aluminum ions and 3 nitrate ions. Charges when the aqueous things dissolve. Perfect. So it looks like that. That's step number 2, the overall ionic equation. And then step number 3, the last step, just like with the double replacements, we are looking for spectator ions. They are spectator ions, so they only can be charged things, right? And in single replacements, usually we only have 1 spectator ion. So when we look at this equation, aluminum here was a solid piece of metal. Aluminum here is now in solution because it's aqueous, and so that is very much different than aluminum in solution. And so those guys, they play in the reaction, we leave them alone. The silver here was floating around in solution. Now we have pure solid silver, and so that guy also changed. He is going to participate in the reaction. Our spectator ion here is the nitrate. We have 3 nitrates floating around in solution, 3 nitrates floating around in solution at the end, and so those go away, and our net ionic equation looks like aluminum plus 3 silver ions reacting to form 3 silvers and an aluminum ion. It'll look like that. Is it balanced? The answer is yes, because we balanced it up here. If we keep those coefficients the same, then that thing works out just fine. The other way to check, right? We have a total of plus 3 on the reactant side for the charge. We have a total of plus 3 on the product side for a charge, and so that's another good indicator that we're already balanced. That's our net ionic equation for the single replacement reaction. Only one spectator ion there. That happens to be the nitrates. Good, so how would we do this a little quicker? Here it comes. Turnings, I think we talked about before break. Turnings are like little pieces of ribbon, almost like tinsel on a Christmas tree, little thin pieces of ribbon. So this is magnesium turnings. They're solid pieces of magnesium. So solids always play. That magnesium is going to play as a solid. It's going to be added to iron 3 chloride. Which one of these is always going to be a spectator ion? That's the chloride. If there's no silver, mercury, and lead, it is worth looking back to see that there's no silver, mercury, or lead. And so because there's not, that chloride is going to be our spectator. So we would chop that part. And we would have those iron 3 ions that were going to participate from the solution. So that's the front half of the reaction. What's happening here is magnesium is coming in to this single replacement reaction and kicking the iron out. And iron is going to be left all by itself. All by itself, iron is a solid, no charge on it. And magnesium is now paired up with that chloride. And that magnesium chloride is soluble, so we will have those magnesium ions floating around in solution. Good. Is it balanced? The answer is no. There are one iron on each side and one magnesium on each side, but those charges not being balanced tells us that the equation needs to be fixed. So to fix those charges, we need to find the least common factor of greatest multiplicity between the charge of 2 and 3. That's 6, and so we're going to put a 3 here in front of the magnesium to give us plus 6 total on that side. And a 2 in front of the iron would give us plus 6 on that side. When we do that, we then have to go back and balance the number of atoms. So 2 irons there, we balance with 2 irons there, and 3 magnesiums would balance with the 3 magnesiums on that side, and that would give us our net ionic equation for that last problem. I don't know how quickly you can get to this, where you look at the equation and can get right to the answer. It's a process, right? And so don't be afraid to do a couple problems all the way through in order to get to this. It's not dumb if you do the process and you get the right answer. There's folly if you don't do the process and get the wrong answer. And so take your time and work through them. And if you have questions, you are welcome to email me and get a hold of me. We will talk to you soon. Bye.